Okay, so I hope everybody can see my screen. So, of course, this is a virtual training week because of the following issue. So, normally there would be maybe 30 or 40 of us together in a cluster where everything was already set up and you'd all be working at machines that where we'd installed the code and we tested everything. Obviously, that's not possible because of the coronavirus. So that has advantages as well as disadvantages. So of course that means that more of us can all get together. But of course, it's also a completely new thing for us. So our training weeks in the past have been very much in person. So this is the first big virtual one that we've run. So what we're trying to do in this workshop is to convince you that biomolecular simulation is a useful and fun tool for understanding structural and molecular biology, and that doesn't matter if you're a simulator, a theoretician, or an experimentalist. So we believe that everybody should be able to get something out of biomolecular visualization and biomolecular simulation. And of course, one of the reasons that we're so keen to have such a diverse group of people using biomolecular simulation is that it gives us a multidisciplinary community that can exchange ideas and expertise. So we'll have a richer, more enjoyable community if it isn't just people who run simulations, it's also people doing experiments, it's also people who are maybe more interested in the physics or the chemistry side. So we need contributions and ideas exchanged with everybody. And that's one of the things that we'd like to promote with this workshop, and of course with our other activities as CCPBioSim. So the third one, which for me is particularly important, is to appreciate just how beautiful biomacromolecules are. So I'm actually a theoretical physicist, but I've been unable to leave biology since I started working on it because it's just so unbelievably beautiful and so unbelievably rich and complicated, but that's what makes it lots of fun. So we want you to ask lots of questions. We want you to interact with us as much as we can all achieve, given the medium, given the fact that we're not all in a big room together. And no question is ever silly. And the main thing that we want to do is all try and hang out together and have fun. So this is the first time that we've run such a big virtual workshop. So there are things that of course might go wrong. So here I made a list of all of the things I could think of that might go wrong. And these are my top worries. So somebody having poor internet connectivity, so that might be, I mean, the worst would be the hosts. But of course, also it's a problem if you guys have got poor internet connectivity. Another issue is, of course, we can all get lost in Zoom. I've got lost in Zoom this week, so that's another issue. So you will notice as you progress through the training week that we've got a number of different types of technology that we use to deliver the training. So some of that is cloud. So we're using the cloud. We're also using servers. So of course this is all technology. Technology can go wrong. This is the one that worries me most, number 5, is we really want to hear from you, and we really want to answer your questions, and we really want to help you out. But it is very difficult to know how to do this effectively when we're in such a large group. So we do really want to be as interactive as we can be, but if we're not answering your questions, that's not because we don't want to, that's because somehow we just haven't managed to, you haven't managed to get to us, or we haven't managed to get to you. So please do persist, because we really, really do want to chat. There's no point in having such a wonderful group of people from so far away and not be able to talk to them. So we do want to talk to you. So if we are slow, then please bear with us. The other thing that worries me too, and this is one of the problems with online meetings, is of course normally you'd all be having coffee together, you'd all be having biscuits, chatting with each other, and it's a lot more difficult to do that in a virtual environment. So if you do get the opportunity to, in the breakout sessions or during the workshops, to talk to each other as well as to talk to us, then please do, because that will make the whole experience richer for everybody. So I want to remind you that this is actually an experiment inside an experiment. So this is not the first time such a thing has been attempted. So in William Shakespeare, of course, in Hamlet, there's famously a play within a play. And in quite a lot of artwork, so this one's one of my favourites because I'm a huge fan of William Hogarth, you have paintings inside of paintings that tell some of the story. And that's what's going on here. We're talking about computational experiments, but this is itself a computational experiment. So thank you so much for taking part, and let's see what happens over the next week. I hope we all enjoy ourselves. I'm sure we will. So thank you very much for joining us. Okay, so I'm going to try and start by giving a sort of conceptual overview of biomolecular simulation and how it works, how we might go about doing it, and why we might want to do it. So that's what I'm going to try and do in the next half an hour or so. And at the end of this talk, I'll be answering questions, and I hope there'll be lots of time for questions. Sarah will be keeping an eye on your questions, so do please type them in the chat. Okay. So the first thing we have to think about if we want to construct a model of a biological molecule is, what is it like? What is its physics? And on the left-hand side is a lava lamp. And this is how I generally imagine proteins in my own mind at the coarse grain level. So one of these blobs is how I think about a protein. So it's a soft matter object. It's not a static thing with a predefined structure that never changes. Okay. And in fact, biomolecules can change shape dramatically just because of thermal motion. And it's very difficult for us to see these shapes in any other way apart from atomistic simulation, because most of our structural tools, such as X-ray crystallography and now increasingly cryo-EM, tend to give us a single static snapshot. You can get some dynamic information from an NMR, but it's not at the atomistic level unless you are able to put in your restraints and solve your structure. So this is actually an MD simulation of the microtubule binding domain of flagelladymine that I ran based on a solved NMR structure. And you can see that the molecule changes shape quite a lot. This is an atomistic molecular dynamics simulation. So in this particular talk, I'm going to concentrate very much at the atomistic level. And arguably, atomistic molecular dynamics is the best established tool we have for biomolecular simulation. And what atomistic molecular dynamics does is it shows how biomolecules change shape due to thermal fluctuations. Okay, so let's play this one. So this is an MD simulation of the helicase associated with SARS-CoV-2, run by our helicase consortium of volunteers. So let's just play that again. This is the helicase here. You can see there's some bound RNA in here and the ATPs at the top. And the molecule continuously changes shape due to thermal fluctuations. And this was based on a crystal structure that had one static snapshot in it. So the reason that it's important that the biomolecule changes shape is, of course, if we're interested in molecular recognition takes place on the basis of shape, and chemical complementarity, then the fact that our biomolecule is continuously changing shape means that if we want to design any drug molecules, if we want to understand mechanism, we're thinking about a moving target. So we really want to understand what the consequences of these dynamic motions are. So an MD simulation, it's a bottom-up physics-based model. So it combines classical mechanics, so the protein moves in accordance with Newton's equations of motion, classical mechanics, and the detail, the chemical detail, is taken into account by what we call an MD force field. And in general, MD force fields are obtained by running quantum mechanical calculations, so very detailed calculations on tractable molecular fragments, building up this force field, and then those parameters are fed into the classical model, which then enables the proteins to move. So in principle, we can do all sorts of things with this because it's a physics-based model. We know forces, so we know energies. So we can, in principle, predict the binding energy between our protein and a ligand or a binding partner. We could calculate how that protein responds to an external force. We could look at conformational changes, etc., etc., etc. So in principle, this is a hugely powerful tool. But I like to argue that simulation is just the same as any other biophysical tool. And you won't find a biophysical tool anywhere that has resolution over all the time and length scales you're interested in, or that does everything that you want it to do. Biomolecular simulation is no exception, unfortunately. There are limitations, and we'll discuss these throughout the talk. So in order for us to start a biomolecular simulation, we need to know the folded structure of our protein. And to do that, what we do is we go to the amazing, phenomenally amazing resource, the protein database. And this is what I picked up from the front page of the protein data bank. I think it was on Saturday. And I definitely recommend that anyone who hasn't done so takes a look at Molecule of the Month, because it's very beautifully presented and also extremely interesting and accessible write-up on all of the proteins that it covers. So we go to the protein data bank and download our file, but we also need to be aware that protein structures are under continuous re-refinement. So it is a good idea, if you're downloading a protein and looking at it for the first time, to also look and see if there's an entry in PDB redo. And we're having a talk tomorrow by Tristan Kroll, who's going to cover some of these issues in more detail. So we need to go and get our protein structure. If we're interested in a short peptide that we don't think has any secondary structure, or A or B form DNA, then we can actually build these, if we so wish, in a molecular building program. But if we want to look at a protein, we really have to get a structure from the PDB or produce a homology model. So our proteins are soft matter objects at the mesoscale. They are these blobs that change shape due to thermal fluctuations. But if we want to construct an atomistic model of them, we have to shrink down and think what the atomistic structure on the inside of that blob is actually like. And of course, proteins are long polymer chains made up of 20 naturally occurring amino acids. They're extremely chemically diverse, and it's these chemical properties that determine the folded structure. So we need to be able to capture them. So I've represented here a very short, in the box here, I've represented a very short amino acid chain containing a selection of amino acids with distinct physiochemical properties. So we need to be able to capture things that are polar, charged, titratable, and hydrophobic. And we need to be able to capture the topology of the molecule. So that means its covalent bonds. So we need to represent the covalent bonds. And we do that by representing each atom in the system as a classical ball and the bonds between them as classical springs. We have to have electrostatic interactions because we need to be able to represent charged and polar groups. Of course, we need van der Waals forces or London dispersion forces in order to capture the cohesion of molecular structures in the core. We probably need to worry about hydrogen bonds and also hydrophobicity. So the top three, covalent bonds, electrostatics, van der Waals forces, are implicitly included in the force field equation, which you will see. The hydrogen bonds and the hydrophobicity are not. These are both emergent properties. So this is our MD force field function. And the main thing that you have to take home from this picture is that the force field function is very complicated. So we've got our covalent bonds that can stretch, our angles that can bend, and our dihedrals that can rotate. We've got van der Waals forces and electrostatics. So you don't need to understand this equation, you just need to see that it's very complicated. And the other thing that you need to note is that there are lots and lots of these little parameters that are equilibrium, theta equilibrium, these epsilons in here and these charges in here. So all of these little parameters that are present in your force field function, these are your force field parameters. And the reason that you need to understand that this is so complicated is because I just want everybody to get an appreciation of quite how difficult it is to define a molecular dynamics force field. There are many, many, many different parameters that we need to include. And this, fortunately, has all been done for you by tools like CHARM, AMBER, NAMD, GROMAX, etc. Okay, so how does classical molecular dynamics work? So we define this force field function, we define all of the parameters in our force field, we represent our atoms as classical balls and the covalent bonds as springs. And then what we do is we calculate the force on each atom as a result of every atom in the system using the complicated force field equation. And then we move each atom for a very small time step dt. The force on it is going to be different then because all of the interatomic distances are different. So then we calculate the force again for another short time step to t, move the particles, do the same thing again, move the particles, and what we end up with is a movie of our biomolecule changing shape. So this time step that we use to calculate how far the atoms have moved each time, in order to maintain the stability of the simulation, this time step has to be very short. So typically 2 femtoseconds, that's 2 times 10 to the minus 15 seconds. And of course, we know that protein dynamic timescales, folding, unfolding, will be arguably the slowest dynamic timescale. This takes place over timescales of maybe milliseconds. So we've got this massive gap in timescale between the time that we need to include to actually maintain the stability of the simulation, dt, which is 2 femtoseconds, and the timescale that we want to watch our biomolecule over, which would be at minimum 1 microsecond. So that means that to get 1 microsecond, we need 10 to the 9 iterations. And remember, we have to calculate the force on each atom as a result of all of the other atoms every time we evolve our time step dt. So this quickly becomes a really, really big calculation. And that is actually the principal limitation of molecular dynamics, is the computationally expensive calculation. So inside this force field, what it's doing is it's capturing chemical diversity by assigning what we call atom types and partial charges to each atom. So the atom type is a really crucial concept. It determines the valency of your atom. It determines what all of its bonded parameters are, so how stiff the springs connecting it to its other covalently bonded atoms are and how long that bond is. Your atom type also determines your van der Waals parameters. And so I've just tried to highlight a few here. So here we have an aliphatic carbon here, and that's of atom type CT. And that is a different atom type to an aromatic carbon because it has a different hybridization that is in this aromatic ring here. So your atom type determines your valency, it determines your van der Waals interactions, and it determines all of your bonded parameters. Then separately, we assign each atom a partial charge. So for example, of course, this thing here is charged, so we have to make sure that these atoms carry a net positive charge here. This hydrogen here is very polar, so this has a little delta plus on it. And this oxygen here is polar too, so it has a little delta minus on it. And obviously the partial charge associated with the carbons and hydrogens in the aromatic ring, because that's non-polar, they're going to be pretty close to zero. So the idea of a molecular building tool, like for example the charm GUI, like XLEAP, like the building function in Chimera and in VMD, what they do, crucially, is they contain what is known as residue templates. So these residue templates have pre-programmed into them all of the connectivities and force field parameters that the molecular dynamic simulation program is expecting for that residue. So if you look at your PDB file, you'll see that the residue names are present, and that each residue is associated with a set of atoms. And what these residue templates do is they look at all of the atoms for each given residue and make sure that they all match. And if they do all match, then your program will be able to construct you the files that you need to perform a simulation. So the fact that these building tools have got these residue templates embedded means that to some extent anyway, the chemistry is sort of taken care of for you. That doesn't mean that you can get away with not thinking about it, but it means that you don't have to worry about it every single time. A lot of it is automated. Okay, so what do we have in our simulation cell? So we start off with our biomolecule, and then we'll also add counter ions to that. So positively charged sodium ions, positively charged potassium ions, maybe chlorine, normally for the negatively charged ions. I generally run my simulations in about 150 millimolar of either potassium chloride or sodium chloride. And then the other thing, of course, we need is the water. So we end up with this simulation box with our biomolecule in here, surrounded by water. Now, I've put this little weird diagram at the bottom to remind me to tell you that in MD simulations, in molecular dynamic simulations, we use periodic boxes. So that means that if a molecule comes out of one simulation cell, if it comes out of the simulation cell through natural diffusion, it just comes in the other side. So we need our periodic box to be sufficiently big. I normally use about 10 or 15 angstroms. It needs to be sufficiently big that these periodic images don't see each other. Otherwise, that will introduce artifacts into your calculation. So one of the really interesting conceptual aspects of biomolecular simulation is that each trajectory you obtain is stochastic. So this means that if you run an MD simulation and then you run exactly the same MD simulation again, except with tiny different starting conditions, you'll get a completely different answer. And I've tried to depict that with this random artwork here, which shows particular random paths through conformational space. So that each one of these represents the trajectory that you could possibly obtain through conformational space. And of course, you need lots to start in lots and lots and lots of different places in order to fill up this conformational space and see everything that you might want to see. And of course, every single trajectory is equivalent. No one is better than the other. And I've tried to depict that on the left-hand side here with 3 completely equally valid representations of the god Loki, who's the god of mischief and chaos. But the fact that we get all of these potential trajectories means that we absolutely have to run, whenever we can, repeat simulations. So what we would do is we would run our first MD simulation and check that we were happy with it. If we are happy with it, then we'll run it again as many times as we possibly can. So ideally, we'd run it many thousands of times. We're probably not going to be able to do that because we won't have the computational resource. So we might run it typically 5 times, something like that. And we do that by using different random seeds that we assign at the beginning of the simulation to give you a different arbitrary set of atomic velocities corresponding to the temperature that you want to run the simulation at. So running these repeats is really, really important because you won't necessarily get the same answer when you run the simulation again. And that doesn't mean that the first one is wrong. Everyone is equally valid. It's just that paths through conformational space, the trajectories, the movies that you see of the biomolecule changing shape, these trajectories are in some way stochastic. They're random because of the randomness of thermal noise that generates this motion in the first place. So just to show you an example of where this was very important, this is actually some of our quite old work now actually on DNA mini circles. So these are trajectories that were 50 nanoseconds in length, which now seems very short, but these were very big systems actually at the time. So these are 4 DNA mini circles, and each one is under stress. So they're negatively supercoiled. So they're under torsional stress, each one of these circles. And when DNA is under negative torsional stress, that can melt the hydrogen bonds that are holding the 2 strands together. And when we run these simulations 4 times, exactly the same, we actually see different things. So in example A, the DNA remains intact and there are no broken hydrogen bonds. And the same thing happens for simulation D. But in simulation B, we find that actually there are some broken hydrogen bonds. And in fact, hydrogen bonds in simulation B break in 2 different places. We also see broken hydrogen bonds in simulation C, but this time only once. So you can see that we need to have these repeat trajectories in order to build up a picture of what the system is going to do, because if we just run one simulation, we don't get that coverage of conformational space that you saw we needed by having all of the different random lines starting in different places. So the thing that almost everybody really wants to be able to do with biomolecular simulation is to calculate binding free energies, particularly between proteins and ligands. So this is a long-standing issue for biomolecular simulation because we are as yet unable to always provide a quantitative account of what these free energy changes should be. So there are some really nice tools like free energy perturbation that are capable of doing this for ligands that are very similar. So you can calculate free energy differences, but in general, it's really, really, really hard to calculate binding constants from molecular dynamic simulation. And I've tried to explain in this slide why that is, okay? So your binding constant, Kd, depends on the Gibbs free energy change that happens when your ligand binds to your protein. And your Gibbs free energy change is made up of two terms. It's made up of an enthalpy, which I think of as being the chemistry part. So your enthalpy is more thermodynamically favourable, will prefer the binding of the ligand if there are lots of favourable hydrogen bond interactions, favourable electrostatic interactions, lots of nice van der Waals interactions. And if the binding of the ligand or the other protein, if you're forming a protein complex, doesn't induce that much conformational change. So the structural distortion isn't too great. So that's the enthalpy term, and that's all about the chemistry. And arguably, give or take caveats with force fields, no force fields perfect as we will describe, but give or take our caveats with force fields, we're reasonably good at calculating this enthalpy term. And that is what you would get if you took a protein structure, a ligand structure, and from a static snapshot calculated the interaction energy between them using an MD force field program. The problem is with the second term, the entropy term, so this T delta S term here, and this is what I think of as the physics term, and this is all to do with biomolecular flexibility and also hydrophobicity, so what the solvent is doing. And your entropy is the number of conformations that the system can adopt. So thermodynamics favours diversity. So thermodynamics drives systems towards situations in which there are more conformations. So the problem with the entropy term is because it's all about the amount, the volume of conformational space that the system can explore, if we don't explore every single possible thing that our biomolecule can do, we get this entropy term wrong. And that is, of course, extremely challenging because of the timescales that we can achieve with molecular dynamic simulation, which is in turn because of the computational expense. So the reason, arguably, that we are not great at calculating quantitative binding free energies is because of, firstly, limitations in our force fields that mean that our enthalpy isn't quite correct, but arguably more disastrously, the fact that we can't explore all of conformational space. Nevertheless, of course, docking and computational exploration of ligand binding is extremely valuable. And we hope, still get insight into the molecular recognition process, even if we don't get the same quantitative answer as you might get, for example, through ITC experiments, thermocalorimeter experiments. Okay, so this can cause additional problems. So this is moving on to very briefly to some slightly more advanced topics. So this is a photo that we took when we went walking in the Scottish Highlands. And proteins in the Scottish Highlands have something very important in common, is that it's a lot easier to wander around the valley than it is to climb one of these mountains. And it's absolutely the same when you're thinking about conformational space. So the probability that a protein can adopt a shape with a particular energy is exponentially smaller if that energy is really big. So that means that proteins are exponentially less likely to be found at the top of a hill than in a valley. And that means that simulations can get stuck in particular regions of conformational space. And this is one of the reasons that we're not so great at calculating the entropy, because we end up getting stuck in one valley and we never ever see what's over the other side of the mountain. So there are some tools for getting around that, and these are advanced tools. So one way is simulated annealing or replica exchange, and I've got another Banksy here to represent that. So what these tools do is they put heat energy into the system to try and get it to climb up over the top of the mountain and help it escape from its minimum. Another thing we can do, and this is a very dystopian vision of what will happen during global warming if sea levels continue to rise. So we have this tool called metadynamics or conformational flooding. And what that does is it sort of floods the valleys of our conformational surface, so where the protein can explore, using a biasing potential that stops the simulation from staying in the valleys and sort of pushes it up the hills, if you like. The other thing that we can do is use steered molecular dynamics. So in steered molecular dynamics, what we do is we actually put a force on the molecule. So here, when I ran this one, pulling apart 2 bits of DNA, I had a force on one end of the DNA and a force on the opposite strand at the other end of the DNA, and I pulled the thing apart, and that induced a conformational change. So one of the really fabulous things about biomolecular simulation is that there's a huge wealth of contributed open source tools for building, visualizing, running and analyzing your results. And I can't possibly cover all of them and give even the ones that I've touched upon here enough credit, because the community really has made a huge effort to make these user-friendly, easy, accessible, and also very, very beautiful too. So I've just picked a few highlights here. So visualizers, we have PyMol, and there's always an open source version of PyMol. There's Chimera, and Chimera's particularly useful if you're also doing with cryo-EM structures, and it will output AMBER input files so that you can run an AMBER simulation. Want to give a big shout out to the Charm GUI. I think the Charm GUI is arguably one of the most popular builders. It's absolutely superb. VMD that we're going to play with in a minute. So that is it's a visualizer. It's my favorite for visualizing trajectories, but it's also, you can also use it to build NAMD simulations if you want to run a NAMD simulation. So it's both a visualizer and a builder. And many of them actually will build systems for you as well now. So programs, so GROMACS is arguably the most popular molecular dynamics program. It's fast, flexible and free. Another one will be NAMD, that you can build NAMD files through VMD. I personally use AMBER, and the demonstration I'm going to give after lunch is an AMBER demonstration, and I've chosen to use AMBER because, in my opinion, the way in which you construct your input files requires quite an in-depth knowledge of the concepts of things like atom type, residue templates. So I think even if you're not going to use AMBER as your chosen simulation tool, it's sometimes quite useful to see how these things are constructed, so that it might help you debug problems that you might have with other systems and using other tools. So just to point out that AMBER tools, which contains Sander, which will run an MD simulation, is completely free. AMBER PMEMD, which is the fast one, the fast multiprocessor one, and AMBER PMEMD CUDA, which is the one that runs on GPU, that requires a license if you're in a Western country. It's free if you're not in Europe or the US, or maybe Japan, I think. But it's about $300, so it's a minimum cost. So I haven't talked very much about coarse grain simulations, the simulations where we don't represent all the atoms, we collect the atoms together into groups. So Saima Khalid is giving a talk later on today, and she uses a lot of coarse-grained MD. It's extremely useful, and I'm giving a big shout out here to Martini, which is arguably the most popular one and is used a lot for membrane protein simulations. The other thing that we're very lucky to have is a wealth of networks and communities. So we have the MOL SSI, and you can go and have a look at their resources here. BioExcel is an EU one, and of course us, CCPBioSim, based in the UK. And if you visit any of these websites, you will find a vast resource of tutorials, tools that you can use, advice, sometimes trajectories, etc., etc., etc. So there's lots and lots of support out there. So I just want to emphasize that when you're doing your MD simulations, no force field is going to be perfect. And in the amber demonstration, I will parameterize a ligand, but I'm going to do it in a very, very quick and dirty way. To do it properly requires a lot longer and probably chemical expertise, but certainly doing for a small ligand, just having a quick go works okay. So there are more detailed simulation methods. There's this idea of polarizable potentials. So, you know, in our MD simulations, the partial charges we stick on each atom, those are fixed and they never change. Whereas, of course, in reality, as your molecule changes shape, or maybe a magnesium ion drifts near a part of your nucleic acid, that will actually polarize your system, and that is not included in a standard MD simulation. So that's one of the ways in which you could improve your description if you're worried about your force fields, but these are currently very expensive. We're going to be running a QMMM workshop on Friday, and this is an advanced method that you need if you want to do any chemistry. So of course, in an MD simulation, all of our covalent bonds are perfect springs held together that hold the atoms together, and those springs cannot break. If you want to break a covalent bond, then you need to use some sort of QMMM method. So biomolecular simulation is for everyone. So my personal view is that anybody who does structural molecular biology should do some form of visualization and potentially simulation. So I've tried to sort of set up a list of things that you know, if you just want to dabble, then you can visualize your proteins with VMD or Chimera or Pymol. You can make mutations. You can do a simple structural renucleation and a simple docking. And I would argue that everyone who touches a protein experimentally or as a theoretician, if you're a theoretical physicist, for example, then you should be able to use some visualization tool to explore your structures and to help you think about things. So intermediate would be to run a basic MD simulation of your protein or your piece of DNA or your RNA using something like Amber or GROMACS, be able to do simple analysis and be able to do simple parallelization. So this would need a GPU workstation. So GPU workstations are pretty cheap now. I bought a gaming laptop with a nice graphics card for under £1,000 at the beginning of lockdown. So and a GPU makes a huge difference. You can also run these things on small clusters if you don't have a GPU. So of course there are also advanced. If you really getting into your biomolecular simulation, then you might want to do some things that are more advanced. So if you've got a very large protein complex, then that might run too slowly on your GPU. It might even be too big for your GPU. So then you might need to get some supercomputer time. If you want to use any of those enhanced sampling tools that I spoke about, those are very computationally expensive. They require expertise. Then I think, you probably want supercomputer time as well. These are advanced tools. If you want to develop new methods, QMMM, etc., etc. So if you can get past stage 1 and to some extent get past stage 2, then certainly in the UK, we have a pipeline to get you onto supercomputer resources through HEC-BioSim. So this is a consortium that allocates supercomputer time either on Archer, which is our UK CPU supercomputer, or JADE, which is GPU. You have to write a little proposal. I describe it as supportive peer review, and Simon will talk a bit more about that later on in her talk today, because she's chair of HEC-BioSim. So this is why I argue everybody needs biomolecular simulation. So if you visualize your system, and if you take the time to look at it really carefully and explore it, it can reveal unexpected truths and provide a new perspective. And what this is here actually is it's a fossil inside of coal. So the coal miners in Durham have described these amazing fossilized forests that they occasionally saw as they were doing their coal mining. And it's obvious that they should be there, but unless you take the time to look, you'll never realise. So visualisation is, I would argue, absolutely key, and everybody should be doing it. So, of course, the other thing you can do with a model is you can test your ideas before you try them in the lab. And this crazy thing on the left-hand side is a steampunk coffee maker. And I think you'd all agree that you probably want to build a prototype of this before manufacturing it, because it doesn't look to me to be a particularly practical idea. Simulations can also help you identify little mistakes and little errors in very big and complicated tasks like structure refinement. And I'm not going to talk about that at all, because I refer you to Tristan's talk on Tuesday, where he's going to describe a Zelda, which is exactly for doing just that. And of course, biomolecular simulations are physics-based models, so they contain some element of ground truth. The emergent properties, so how the system behaves over time, over many replicas, this is not so reliable, but certainly, you know, if the thing that you're trying to build breaks the rules of chemical valency, then it's not the simulation that's wrong, it's what you're trying to do. So building these type of models can be really, really helpful for identifying problems and mistakes. And so the main thing we get from model building is insight, especially if it goes wrong. So if you build something and you consider it to contain the best representation of the system you can imagine, and it doesn't do what you expect, you learn something. And you think, well, why didn't it do that? And you can look at the simulation and you can work it out, hopefully, and then you will learn something new. You will have your previous attitude about what's important maybe